is part 3 of your exam review, and it's on Newton's laws of motion. First thing, Newton's first law. An object at rest will remain at rest, and an object in motion will remain in constant motion, unless acted on by an outside force. So it's the nature of matter to keep doing whatever it's doing. To change motion requires unbalanced forces. Continuing with the same motion does not. Balanced forces result in no change in motion, no acceleration. This does not mean no motion. It means no change in motion. This is also called the law of inertia. Galileo was the first person to develop the idea of inertia, and Newton came along after Galileo and built his first law based on the ideas that Galileo had published. Galileo did thought experiments, like if I roll a ball down an incline and there's no friction, what would happen? So if I have an incline and there's no friction and I roll a ball down, he proposed that that ball would just keep going and keep going and keep going if there were no frictional force to make it stop. So no force acting means you continue motion, not that there is no motion. The definition of inertia is a resistance to change in motion, and mass is a measure of inertia. So mass and inertia are very closely related concepts. Newton's second law is where the math comes in. And we need to talk about forces a little bit before we get to it. There are two main types of forces, contact forces and field forces. Field forces are also called at a distance forces because they can act when the objects are at a distance. Contact forces require the two objects be touching. Well, that's why they're called contact forces. So friction, tension, the normal force, spring forces, and applied forces, those are all contact forces. Field forces are forces that can act when the objects are not touching, and the only ones we have are magnetism, the electric force, and the gravitational force. Newton's law says that the sum of the forces equals ma, equals mass times acceleration. So if I exert a big force, I get a big acceleration. If I exert that force on a big mass, I get a smaller acceleration. So the force and acceleration are directly proportional, and acceleration and mass are inversely proportional. This symbol, that is the Greek letter sigma, and it means the sum of, means add them up. So it is the sum of the forces, or the net force, that actually causes the acceleration. Forces are vectors, and so we call this a vector sum, because we don't just add them up. I mean, sometimes you can, but depending on the direction, you might have to do some trade. The acceleration that's caused by a force is in the same direction as a force. The direction might be as simple as a plus or minus sign for one-dimensional motion, or it might have a degree measure or a compass direction, like the force acts towards the north. Let's talk about mass and weight. Mass and weight are not the same thing. Mass is measured in kilograms, and it's how much stuff is in something. Weight is the gravitational force on an object, or on the mass of an object, and it's measured in newtons. Mass, kilograms, weight, newtons. Since a force is equal to a mass times an acceleration, and we're talking about the gravitational force, it's equal to mass times the gravitational acceleration, little g. So weight always acts downward, and example, find the weight of a 10 kilogram object. So the weight equals mg equals 10 kilograms times 9.8 meters per second squared, and so that's 98 newtons. Find the mass of a 20 newton object. Well, if weight equals mg, then mass is equal to the weight divided by g, and so that's 20 newtons divided by 9.8 meters per second squared. 20 divided by 9.8 equals 2.04. And I'm going to say 2 kilograms. More Newton's second law. The normal force. Normal means perpendicular to, and for the force, it means it's perpendicular to the surface. So a normal force is a reaction force. If I have a book sitting on a table, that table exerts a normal force on the book, and we label it N for the normal force. It's always perpendicular to the surface. It can equal weight, but it doesn't have to equal the weight. If I have an object on an incline, the normal force is perpendicular to the surface again. It's not always up, and this would be a case where the normal force does not equal weight. Tension is a force that's exerted by a rope, a cord, a cable, a string, anything like that, flexible cable, ropey things. Friction, and tension, we would typically label T. So if I have a box that's being pulled by a rope, then I would label that force as a tension force. Friction is a force that resists the motion of two objects sliding against each other. There are two kinds of friction forces. There are static friction forces and there are kinetic friction forces. Static friction forces resist the beginning of motion. They happen before motion begins. Kinetic friction happens when the objects are already sliding. An applied force is usually a force that a person applies or an object applies. It's generally one of the forces that we haven't talked about. So George, that's supposed to be George's head. George pushes a box across the floor. We would call, if I'm drawing a free body diagram, we would call that an applied force because George is applying a force. Calculations, you need to be able to use this equation to solve for any of the three variables given the other two. So let's look at some examples. Find the acceleration of a 20 Newton if a 20 Newton net force acts on a 10 kilogram object. Acceleration is force divided by mass. F equals ma, so divided both sides by m. And that's 20 newtons divided by 10 kilograms equals 2 meters per second squared. So adding forces, direction matters. In simple problems, direction will be a plus or minus sign. But if the problems are two-dimensional, you have to use trig. See the two-dimensional kinematics exam review for the details of adding vectors. So that would be exam review part 2. So if you look at that, you can, there's a whole adding vectors section. So add the following. The answer needs magnitude and direction. So I have a 10 Newton force that's north and another 10 Newton force that's north. These are both 10 Newtons, and they add to be equal to 20 Newtons, also north. 10 Newtons north and 10 Newtons south would add to 0. And 0 would have no direction, but they would cancel out because they're in opposite directions and they're the same size. 10 Newtons north and 10 Newtons east. We have to use Pythagorean theorem. That's going to give us a resultant in this direction. So the magnitude of the resultant is going to be equal to the x component squared plus the y component squared, and then take the square root. So 10 squared is 100. That's going to be 200, and the square root of 200. So it is 14.1 newtons, but the direction, and in this case, I can tell because the components are the same, I can tell that's going to be a 45-degree angle. But if I wanted to use inverse tangent, I'd say the inverse tangent of y over x, inverse tangent, and that'd be the inverse tangent of 10 over 10. And the inverse tangent of 1, use your calculator, is 45 degrees. So theta does equal 45 degrees. So it needs a magnitude and a direction when you add forces. Okay, free body diagrams. Use a dot. Okay, I use squares, but your textbook, the text for this course and the answer expected on tests and quizzes is that we use a dot to represent the object. And the arrows come from that dot representing the forces acting, and they're in the direction that the force would be push or pulling the object. And the length of the arrow represents the magnitude. What does a free body diagram look like if an object is not accelerating? The forces are balanced. You have forces in each direction adding to 0. So I'll say forces add to 0. Like, okay, pretend that's a dot and not a square. So this is an object that is not accelerating because the forces are balanced. Draw a free body diagram, and an object is on an elevator and the elevator is stationary. Well, then there is the weight downward, and there's the normal force upward, and they're the same size because it's stationary, which means it's not accelerating. An object is on an elevator moving with a constant velocity. Again, constant velocity, not accelerating. So the normal force and the weight will be equal and opposite. An object on an elevator accelerating upward. If it's accelerating upward, then the up force has to be bigger than the down force. So the normal force is bigger than the weight. An object is on an elevator accelerating downward. That means the weight has to be greater than the normal force. The acceleration is in the direction of the net force. If I have a little force up and a big force down, the net force is down. An object is moving to the right, slowing down. So if it's moving to the right, slowing down, that means it needs a big force to the left, because the net, if it's slowing down, the acceleration has to be to the left. And there might be a force to the right, but there doesn't have to be. And we're going to go ahead and draw the weight and the normal force. Let's let that be a frictional force and let that be an applied force. So I can tell it is moving to the right. I mean, I can't tell it's moving to the right, but the problem said it is, but it's slowing down, and I know that its acceleration is to the left because the net force is to the left. A hot air balloon is accelerating upward. If it's accelerating upward, then its weight must be smaller than it's actually the buoyant force. You don't have to know that, but whatever upward force it is, and it is the buoyant force, has to be bigger than the weight. So the direction of the acceleration is the direction of the net force, bigger arrow. Finding a force equation using a free body diagram. Write sum of the forces equations for both dimensions. Okay, the sum of the forces in the x equals that applied force minus the frictional force, and that equals ma, x, the x component of the acceleration, and in this case, that equals 0 because the forces are the same size. The sum of the forces in the y direction would be the normal force minus the weight, and that equals m times the y acceleration. That's a subscript, and that also equals 0 in this case because they're the same size. Find an unknown force using a free body diagram. Okay, so if I do the sum of the forces in the y, I get 0 because it's 35 minus 35. Sum of the forces in the x is our unknown. We'll just call it question mark, minus 10 newtons equals ma. And, you find the missing force. I'm sorry, I didn't catch this. Find the missing force, which is what the problem says we're going to do. And let's let the acceleration be 2 meters per second squared. So our missing force minus 10 newtons equals 2 kilograms times 2 meters per second squared. So the question mark minus 10 equals 4. Add 10 to both sides, and our missing force is equal to 14 newtons. What's the net force? In this case, our net upward force is 25, right? 25 newtons because 10 and 15. And then we have a downward force of 20. So the net force is 5 newtons upward. Okay. Third law, for every action there's an equal and opposite reaction. And what that means is that forces are interactions between objects. So you can't have a first object acting on a second without the second acting back with the same force, but in the opposite direction. So a bat hits a ball, but the ball also hits the bat with the same force. And that's an action-reaction pair. The bat hits a ball, the ball hits the bat. Action-reaction pairs are always object A acts on object B, and object B acts on object A. An action-reaction pair only has 2 objects, A and B. The bat hits the ball hits the bat. And you can tell it's an action-reaction pair because there are only 2 objects and they switch places. So if a cart pulls on here's our cart, and here's our horse. Ooh, I don't draw a good horse. Here's the tail. Okay, if the cart's pulling on the horse with the same but opposite force from the force that the horse is using to pull the cart, how do they move? Well, yes, here the horse is pulling on the cart and the cart's pulling back with the same force. But the reason this works is the frictional force, the horse is pushing back on the ground, and so there's a frictional force forward here, and that's bigger than any frictional force here from the wheels. You know, If you tied that horse, I'm just going to say horse instead of drawing one, and the box didn't have wheels, it would be harder for the horse to pull because there'd be a bigger frictional force, and he'd have to dig his heels in and have a really big frictional force. If we put it on a sled, it'd be in the middle. If we put that on a sled like that, and he's pulling it, then this is a smaller frictional force, but still bigger than when they have wheels. But the horse is able to pull the cart because not the forces that are here being different, but because the frictional force that the horse gets with the ground is bigger than the frictional force that the sled or the cart get with the ground. A 100 kilogram gun applies 250 newtons of force to a 0.02 kilogram bullet. Find the force on the gun. Well, it's 250 newtons. The gun pushes on the bullet with the same force that the bullet pushes on the gun, so it is 250 newtons. Find the acceleration of each, and this is where the difference is. Acceleration is force over mass. So for the bullet, you have 250 newtons divided by 0.02 kilograms, and for the gun, you have 250 newtons divided by 100 kilograms. And so this is 2.5 meters per second squared, and 250 divided by 0.02 is 12,500 meters per second squared. Same force, different accelerations. A small mass gets a really large acceleration, and a larger mass gets a smaller acceleration. And that's the end of review 3. Stay tuned for the exam review number 4, which will be applications of Newton's laws.